Okay, so this is an example with a repeated irreducible quadratic, right? A repeated irreducible quadratic. So we know that it has to have two separate fractions because the highest power of the bottom is the second power. So we're going to have, and each of these fractions should have what in their numerators? Something like ax plus b, right? Because the bottom is irreducible quadratic. So what should the second one look like? Exactly. Okay, now to get common denominators, what would you need to multiply the first fraction on the right-hand side with? The top and the bottom of the first fraction is being multiplied by x squared plus 2, right? This will make the bottom of that fraction x squared plus 2 quantity square, and that is your least common denominator. And how about the second fraction on the right, the top and the bottom of that? What should I multiply that one with? Anything at all? Just one, because it already has that least common denominator, right? So I will just have cx plus d multiplied by 1, and I don't even have to mention the 1 in there. So this is the numerator of the right-hand side after we got common denominators, and the numerator of the left-hand side is x squared plus x plus 2. And once again, because an irreducible quadratic is involved, I'm going to go ahead and multiply everything out. So I have ax times x squared, so that's ax cubed, then ax times 2, and then b times x squared plus 2b to be added to cx plus d. Now let's put the like terms together, right? There's only one x cubed term, which I will write up front. Okay, I only see one x squared term. How about x terms? I should combine this one with this one, right? 2a plus c. And the constant with no x's in them, we have 2b plus c. All of this must be equal to the left-hand side. Okay, right away we see something. What is that? There is no x cubed term here, right? This is like 0x cubed, if you will. So what is a equal to automatically? 0. So that's nice to know right away. A is 0. Also, b comes out very simply, right? What is b? The coefficient of x squared, which is just 1. Okay, as to the constant, or let's do the coefficient of x, 2a plus c must be equal to 1. And finally, the constant term, 2b plus c must be equal to 2. Okay, since a is 0, we automatically get c is equal to 1, since a is 0. And since b is 1, what do we get about d? Since b is 1, what is d? 0, right? 2 plus d is 2, so d is 2 minus 2, or 0. So we got all of our unknowns in here. Now we're ready to integrate. Now let me wait for a moment and see if there are any questions about how we got the constants. Any questions at all? Okay, we're ready to integrate. The first step was ax plus b. So our integral is now I equals ax plus b. A is 0, so it's just going to be b over x squared plus 2. And then cx plus d, c is 1, dx. So 1 times x plus d, which is 0. I don't even need to bother putting there, but I did it anyway. Don't know why. X squared plus 2 squared. Okay, I'm going to get rid of that 0. We don't need it. Okay. How do we integrate this? The first part, 1 over x squared plus 2. How do we integrate that? That's arctangent, right? And our a is the square root of 2. So what will the end result be? 1 over a, which is 1 over root 2, tan inverse of x over root 2. And how do we integrate the second part? Use substitution. Take a moment to do that part, please. So you could let u be equal to x squared plus 2. So du is 2x dx. And when you write it in the integral, it's going to look like the integral of 1/2 du over u squared, which is negative 1 over 2 u on the bottom. So that's the same as negative 1 over 2 u. And since u is x squared plus 2, I put it in there. There we have it. Okay, here's one more example with the partial fractions method. The integral of cosine x dx divided by sine square x plus sine x. And there is a similar question on one of the group activities. So the first step should be to transfer this into a polynomial equation or a rational expression without the trig functions. So let's ask ourselves, what would be a good choice for u? Again, since we have the cosine x dx on the top, it would be a good idea to select u be sine x. So its derivative is cosine x dx. So now the integral can be rewritten as just a du on the top and u squared plus u on the bottom. Let's factor the denominator as u times quantity u plus 1. And now this is in perfect position for the partial fractions method. So we're going to have a over u plus b over u plus 1. Since both of these fractions have linear denominators, we just need a constant in the numerator. And again, as always, we need to get common denominators. So multiply the first fraction, top and bottom, by u plus 1, and the second one by u. And since the denominator of the right-hand side will be the same as the denominator of the left-hand side, we just set the numerators equal. And right now, the left-hand side is really the step above, where you have just 1 on the top. So I'm going to set this whole equation equal to just 1. Again, just to illustrate that a little bit better, let me carry it also to the left-hand side here. We have 1 du over u times u plus 1 on the left-hand side. Okay, to determine a and b, again, there is no reason to multiply this out, although we can do that if we wanted to. But for linear factors, it's easier to let u be equal to certain values. Like in this case, let u be 0 and then -1. That will do the trick. So 1 equals, if u is 0, we have a times 1 plus 0. So a is 1. If u is -1, then we will have 1 equals a times 0 plus b times -1. So b is -1. So our integral becomes a over u, which is 1 over u, plus b over u plus 1. Of course, both of these are very simple to integrate. And we get ln of u minus ln of u plus 1 plus c. We can combine them into a single ln while at the same time placing the value for u in there. And remember that u was sine x, so we get ln of sine x divided by sine x plus 1 plus c. And again, the reason I have it in the quotient format is because I had ln a minus ln b. That can be written as ln of a over b. So the moment we got rid of the trig functions, it became a regular partial fractions question. And just at the end, we had to remember to replace u with its equivalent.